Hello, and welcome to Field Lab Earth, the podcast that's all about past and present advances in the fields of agronomic, crop, soil, and environmental sciences. Today we'll be talking to Dr. Budong Qian about simulated canola yield responses to climate change in Canada. What does the future of canola growth in Canada look like? How can we simulate future conditions? What adaptations can we work towards to keep this crop secure? Answers to all these questions and more coming right up. I'm your host, Abby Morrison. Let's talk about science. Hi, Budong. Welcome to the show. How are you doing today?
Yeah, good. Thank you very much for having me.
Good. Welcome. We're going to launch right in here, and you can just tell me a little bit about yourself, maybe your personal and educational background.
I'm a research scientist working for Agriculture and Agri-Food Canada, the Canadian Federal Department for the Agriculture and Agri-Food sector. And I have been working on climate variability, climate change, and their impacts on agriculture, mainly crop production, since 2002 when I moved to Canada. Assessing climate change impacts and developing adaptation strategies for the agriculture sector are very challenging. I obtained my PhD from the University of Lisbon in Portugal. I had my undergraduate and postgraduate education in climatology in China back to the 1980s.
Wow, that's great. And we're going to be talking about canola today. It's kind of a name you might have heard, but for anyone who's unfamiliar with that crop, can you tell me a little bit about it, what it looks like, what it's used for?
Yes, thank you. Canola is one of rapeseed crops. Actually, rapeseed include canola is the second largest oilseed crop across the globe. The plant belongs to the Brassica genus, the botanical family that includes cauliflower and cabbages. The name canola is a contraction of Canada and ola, meaning oil. To own the name canola, products must meet an internationally regulated standard. The seeds are 44% oil, more than double the oil content of soybeans.
Can you tell me more about canola and how it fits kind of into the Canadian economy and agricultural system?
Yes. Canola is the world's only made-in-Canada crop. It was developed by the researchers from Agriculture and Agri-Food Canada and the University of Manitoba in the 1970s. Using traditional plant breeding techniques, Canada accounts for 22% of the global cultivated area of canola rapeseed and exports 90% of its production. Canola cultivation area in Canada, more than 95% on the Canadian prairies, has been expanded from 2.5 million hectares in the late 1980s to 8.5 million hectares in recent years. Seed yield has increased from below 1,500 kilogram per hectare to around 2,000 kilogram per hectare in the same time period. Canola seed production in 2017 reached 21.3 million tons, while it was 3.7 million tons in 1986. Canola has surpassed spring wheat as the dominant crop in Canada. A study released in 2013 shows that Canadian-grown canola contributes 19.3 billion Canadian dollars to the Canadian economy each year.
Wow, that's huge. That's a big deal.
Yes, thank you.
So then what are some of the problems that canola is currently facing as a crop in Canada?
Yes, studies based on crop experiments show that the development of Brassica species responds significantly to the environment, especially to temperature. Heat stress during flowering can result in a reduction in seed yield, an increase of 3 to 3.5 degrees Celsius in annual mean temperature was projected for agricultural regions in Canada by the near future, that's the 2050s, and larger increases in temperature for the distant future, say 2080s. Therefore, the projected warmer future climate is suspected to be unfavorable to cool season crops such as canola. Earlier seeding and higher nitrogen fertilizer application rates are often considered as potential adaptation measures to avoid the heat stress at key growth stage and to meet increased nitrogen demand under warmer climate. However, so far, no comprehensive assessment has been conducted on the potential impacts of climate change and the effects of potential adaptation measures on canola growth and yield, although such studies are necessary for developing climate change adaptation strategies for canola production.
Yeah, and that's kind of what your project here was looking into.
Yes.
So can you tell me, there were 3 specific goals for this project. Can you outline what those were?
Yes, as some of you may know that there are not many crop simulation models currently available for canola. A canola model, the CSM crop growth canola model, included in the decision support system for agri-technology transfer that is abbreviated as DSAT, has been successfully adapted for simulating canola growth and yield in Canada. In our previous study, our objective for this study were, first, to simulate canola growth and yield under distinct climate conditions across 3 locations across Canada, as our previous study was done only for 1 location. The second, to simulate the responses of canola growth and yield and a set of future climate scenarios developed with a regional climate model. And the third, to evaluate the potentials of climate change adaptation measures for canola production in Canada. This study represents a very first attempt to use a dynamic crop model to assess the climate change impacts on canola growth and yield in Canada.
Moving on then to talk about how you did some of this, let's start with those 3 locations that you talked about. Can you tell me what are some of their physical attributes, why you picked them, what they would look like just to the casual observer walking by?
Yeah, 3 Canadian locations, Brandon in Manitoba on the Canadian prairies, and Western Nipissing in Ontario, and Normandy in Quebec, both in East Canada, were used in this study because of the availability of crop experimental data for model calibration and evaluation. Furthermore, Brandon is a location on the Canadian prairies where most canola in Canada is produced. In contrast, Western Nipissing and Normandy are located in the northern edge of current agriculture areas where cultivation of annual crops might further expand.
Yeah, that's super cool. I thought it was interesting, this tension in the paper between, being able to expand where you grow it, but also maybe not being able to grow it as well because of the temperature fluctuations and all that. I thought it was really fascinating.
Thank you.
You're welcome. So now we're getting into some of the things that I had to email you back and forth like 80 times. Because it was really complicated and complex. So we'll just try and maybe take this a little bit step by step. So the first thing that you guys kind of had to do was some field experiments, right?
Yes.
So can you tell me a little bit about what you used those field experiments for?
Yes, thank you for this question. So, we are using a crop model. So a crop growth model is a numerical model that describes processes of crop growth and development as a function of weather conditions, soil conditions, and crop management. Typically, such models estimate times that specific growth stages are attained, biomass of crop components, for examples, leaves, stems, roots, and harvestable products, in this case, canola seeds, as they change over time, and similarly, changes in soil moisture and nutrient status. Crop growth models are developed based on the understanding of the physiological mechanisms of crop growth and development in response to the environment and crop management practices. Field experiments are extremely important for such understanding, for developing the models, as well as for calibrating crop parameters in the models, mainly the cultivar coefficients in the CSM crop grow canola model in this study. Cultivar coefficients were calibrated by running the model with potential values of the coefficients to match the model outputs with measured values in the field experiments. So we need field experiments to support crop modeling studies.
Okay. So the field data was used to calibrate the model to these specific cultivars that you were studying?
Yes, that's right.
Perfect. And then the rest you were going to use to kind of verify that it was working the way that you thought it should, right?
Yes, a subset of those independent data from the field experiments were used to evaluate the calibrated model before the model was used to run simulations with future climate scenarios.
Perfect. Moving on to some of those future scenarios that were studied, there's a few moving pieces with this as well. Let's talk about RCPs. So what are they? Who makes them? What are they used for? Can you talk about that?
Yes. So RCPs, that's abbreviations for Representative Concentration Pathways, developed by Intergovernmental Panel on Climate Change, that's IPCC, used as forcing scenarios to global climate models in climate projections. RCPs are greenhouse gas concentration trajectories based on future socio-economic and technological development that may or may not be realized. The four RCPs, RCP 2.6, RCP 4.5, RCP 6, and RCP 8.5 are named after a possible range of radiative forcing values in the year 2100 relative to pre-industrial values, plus 2.6, plus 4.5, plus 6, and plus 8.5 watts per square meter, respectively. They describe four possible climate features, all of which are considered possible depending on how much greenhouse gases are emitted in the years to come. Two RCPs were used in this study. RCP 4.5 is a pathway that greenhouse gas emissions peak around 2040, then decline, and RCP 8.5 is a pathway that greenhouse gases emissions continue to rise throughout the 21st century. That's about RCPs.
Okay. So these RCPs are used to simulate possible greenhouse gas concentrations, and then you use those in a different model to project potential futures for what the climate looks like, right?
Yes, that's right. So actually, we are not doing climate projections by ourselves. Climate modeling, that's something done by climate modeling groups around the world. In our case, we are using climate scenarios from a Canadian regional climate model called Qian RCM4. So those climate scenarios are simulated by a climate model with radiative forcing from those RCP 4.5 and RCP 8.5.
Okay. So the RCPs are plugged into these regional climate models that are created by these climate modeling groups. And then you took the projection for the regions that you were looking at, but there are some biases that need to be corrected, right?
Yes, and as you know, so model output from climate models could have biases. In this case, we are using a regional climate model. So this regional model, CAN RCM4, was developed and operated by Environment and Climate Change Canada. And actually, so RCPs were used as forcing to a global climate model, and then the regional model was used as a dynamical downscaling tool to obtain future climate scenarios for regional climate change impact studies. As you may know, that bias in climate models often exists and can be attributed to uncertainties in representations of atmospheric physics, boundary conditions, and initialization, inadequate reference data sets such as reanalysis data, climate variability, limitations in input data resolution, and simplifications required due to limited computing capacity. Bias corrections to climate model output as a post-processing step has been used to address this deficiency. While climate models should continue to be developed to improve predictability, current deficiencies in climate models often necessitate corrections of resulting climate biases to make the data useful as input for climate change impact studies, such as for crop simulations. In this study, the equidistant cumulative distribution function matching method was used in our study.
And to do that, you used the historical data from the region, right? Can you tell me more about that?
Yeah, that's right. Historical data actually is important. Historical climate data in the time period of 1971 to 2000 observed at the locations were used as the baseline climate in the bias correction of this regional climate model output. They were also used as climate input to the crop model to simulate canola growth and yield on the baseline climate. So when we are talking about climate change, so we need a baseline climate as a reference.
So basically the way that you know if your bias correction worked is because you're then comparing it to your baseline data, the outputs that you got, to see if they match? Yes, that's right. Okay.
Yes. So with bias correction, the model output can have a good match with historical observed weather data. And then we use the same methodology to bias correct the regional model output for the future periods. So in our case, near future 2041 to 2070, and distant future 2071 to 2100. And then we use those bias corrected, we call the climate scenarios to drive the crop model to simulate canola growth and yield on the future climate. Potential advancing of seeding was taken into consideration in such simulations.
Hello, everyone. I hope you're enjoying today's episode. Interested in learning more? Budong's article, Simulated Canola Yield Responses to Climate Change and Adaptation in Canada, published in Agronomy Journal, is always freely available on our digital library. You can find a link to it in our show notes. Let's get back to the show. So then, after you tested your model, had all of your different inputs to test the various seeding dates and the different climate projections, what did you find? What were some of your results?
Yeah, so what we found from our simulation results, that the growing period of canola from seeding to physiological maturity would be 2 to 5 days short in West Nipissing and 8 to 9 days short in Normandy in eastern Canada due to projected temperature increases and the limited opportunity to shift seeding date. The growing period length could remain unchanged at Brandon on the Canadian prairies due to the potential of early seeding. However, the growing period length would also be shortened at Brandon if the seeding date remained at the baseline. Compared to the baseline climate of 1971 to 2000, simulated seed yield reduction was 42, 21, and 24% in the near future, and of 37, 27, 23% in the distant future, and RCP 4.5, respectively for Brandon, West Nipissing, and Normandy. A larger reduction was simulated under RCP 8.5, especially in the distant future at Brandon and West Nipissing, 44, 33, and 25% for the near future, and 74, 50, and 26% for the distant future. The simulated seed yield reduction was associated with increases in heat and water stresses and rainfall conditions with current nitrogen fertilizer application rates. So we are talking about the simulation results with current nitrogen fertilizer application rates.
So then you were looking for some of the potential adaptations to help. What did you find in regards to that?
Yes. We think that coping with heat and water stresses could be a big challenge for canola production in Canada and the projected climate change, especially on the Canadian prairies. Early seeding new cultivars that are tolerant of both heat and water stress, and improved crop management practices such as more effective fertilizer application and irrigation might be of help to reduce the adverse impacts of climate change on canola production.
In talking about some of these new cultivars, obviously that's one area of future research, but what else do you see as far as future research needs in this area?
Definitely further studies are warranted as uncertainties associated with crop growth models and climate scenarios are large. Meanwhile, crop growth models need to be improved for reliably simulating climate change impacts on crop growth and yields. Crop growth experiments are needed for this kind of purposes.
Sure. And for you personally, what are you looking into for future research?
Yeah, we are using multiple crop growth models, as we said that uncertainty rates to crop models are large. And we are also trying to use more climate scenarios to assist in estimating uncertainty and in developing rigorous adaptation measures to climate change for canola production. We are preparing a more comprehensive assessment of climate change impacts on crop production. In this case, we are talking about major crops across Canada, including canola, using multiple crop simulation models and climate scenarios from 20 global climate models.
Wow, that sounds great. Are you sticking just with canola, or are you looking at other crops as well?
Yes, we are also looking at corn and spring wheat at this moment.
All right. Well, that sounds wonderful. Thank you for all that you do as a researcher.
Thank you.
You're welcome. I have 3 questions left for you. So the first one is going to be, if people want to learn more about these topics, where can they go?
Yeah, I think there are quite a few websites probably people can visit about the crop growth models and DSAT. They can visit a website dsat.net That's about the crop model. And more information about canola production in Canada can be accessed at Canola Council of Canada website. People can also visit Agriculture and Agri-Food Canada website to find more information about scientific research and innovation in the department.
Great. We'll include some links to those in our show notes.
Thank you.
You're welcome. And then second question is, if people want to help with these issues, what can they do to get involved?
Yeah, I think we can show our understanding on climate change and the impacts to the society and to our actions for mitigating adverse impacts of climate change and developing adaptation strategies based on science.
Sure. Final question is, what is one fun fact that people wouldn't know about you if all they had was your research?
Yeah, it's an interesting question. So as I mentioned that, so we should take our share in mitigate climate change impacts. And my family uses only energy-efficient lighting in the household, such as LED bulbs to reduce electricity consumption. And this is environmentally friendly and, of course, also money-saving. I think that everyone can help in mitigating climate change impacts for next generations in a responsible way.
Yeah, for sure. Well, that's all the questions I have for you, but it has been such a pleasure to talk to you, and thank you so much for being on the show.
Thank you very much. Thank you for having me today.
You're welcome. Thank you for listening to Field Lab Earth. You'll find a link to today's paper and other resources for this episode in our show notes or on our website. If you have any questions, comments, or recommendations for show topics, please contact us at podcast@sciencesocieties.org or on Twitter @FieldLabEarth. If you'd like to hear more content like this, please subscribe, and don't forget to rate and review us on iTunes or anywhere else you find your podcast if you like our show. This podcast is a joint production of the Tri-Societies, the American Society of Agronomy, Crop Science Society of America, and Soil Science Society of America. Special thanks to Lobo Loco for the use of their song Spook Castle on the intro and outro of our show. Opinions and conclusions expressed by authors are their own and are not considered as those of the American Society of Agronomy, Crop Science Society of America, Soil Science Society of America, its staff, its members, or its advertisers.